Hello, everyone. Thank you for attending the early session. So my name is Arman Tuha. I'm a graduate student from Oklahoma State University. So today I'll talk about our work in spin squeezing in power law interacting spin model. So what we show in this work is that using fluke engineering, we not only enhance the amount of spin squeezing, but we also actually improve the scaling of the spin squeezing with the system size. So power law interacting systems, so spin squeezing has been done in a lot of power law interacting platforms like Rydberg array, trapped ions, and power law interacting systems can be realized in a variety of cold atomic platforms. And the really nice thing about this platform is that they really offer you a very high degree of spatial control. So you can prepare your state in a layer selective fashion. You even have single site resolutions, and using different techniques, you can actually have site resolved control and probing of the interaction. So motivated by all these capabilities, basically the question that we wanted to ask is how can we use let's say we have a bilayer of power law interacting spin system, how can we use all of this spatiotemporal control and control over the tuning of interaction? Can we use this to improve the spin squeezing? And what I hope to convince you in the rest of this talk is that yes, we can. So let me briefly introduce our schematic model. So we have a bilayer system where we prepare the initial states in the two layers in the opposing states. The two layers are separated by a distance AZ. And just for convenience, I'm going to divide this Hamiltonian of the system into the intra-layer and the inter-layer part, because they really play two very different important roles. So what the intra-layer is important for is that if we choose the Heisenberg point, then a strong intra-layer interaction will protect the state, will gap protect this state to stay in the collective manifold. And if we have this collective manifold, then we can actually write down the Hamiltonian in a simpler way. We can just use all the collective spin operators, and we can write down the interactions in terms of average interactions. So we have the average interaction in the intra layer and also between the two layers. So then what's the role of the interlayer, the second term of the Hamiltonian? So let's further divide this part of the Hamiltonian into further two parts. So you can really think of the interlayer interaction as spin exchange part and the Ising part. And just for convenience, let's perform Ellsworth-Primakov transformation. And if we do that, this is how the Hamiltonian's spin exchange part looks like. And now it becomes much more intuitive that this is the part that's creating the entangled pairs of excitation, if you just compare this with the tumor squeezing Hamiltonian. What about the Ising part? So what the Ising part does, again, if you look at this transformed form now, it's very clear that this is the part that creates the detuning. So, of course, we want the entangled pair creation, so we want this. The Ising part we don't really want, because we don't want detuning. Now, there are a lot of ways you can get rid of this. For example, you could introduce a staggered field, layer selective field. And if you introduce this term in your Hamiltonian, so what this does is that up to quadratic order, it cancels the interlayer Ising term. And what we end up with is this Hamiltonian. So we have the intra-layer Hamiltonian that remains intact, which we need for the system to remain collective. But we get rid of the Ising term in the interlayer interaction, up to quadratic order. But we can do something slightly more clever. We can actually take advantage of the high spatiotemporal control that these platforms offer us, and we can introduce fluke protocol. So you can start from a very simple just Ising Hamiltonian, and then if you apply the pulse sequence in such a way that the x and y components between the two layers, they add up, but the z component, the Ising term, between the two layers, they actually cancel out with time average, so between this and that. So we then end up with this average Hamiltonian, which looks exactly same as this, with one crucial difference, which is that we here have the absence of this term only up to quadratic order. Whereas for the Fluke protocol, we actually get rid of the Ising term from the Hamiltonian level. And what I'll show you in the next slides, in the result slide, is that that's a big difference. So first, we just want to look at the number of pairs, number of entangled pairs. And so the dashed lines are when we use the staggered field, and the solid line is when we use the Fluke protocol. And as you can see that the Fluke protocol does much significantly better in terms of creating number of entangled pairs. We also want to look at the variance. So in our system, we have these mixed quadratures, and the squeezed x's are the p minus, and the x plus squeezed x's. So if we look at the variance in these squeezed direction, then we see that for variance as well, the Fluke protocol case does significantly better. In fact, it can be orders of magnitude better compared to the staggered field case. Well, at least for alpha 0 and alpha 1, so the infinite range and the longer range case. Not so much yet for alpha 2 and alpha 3, not for the shorter ranges. And the reason that these are not too different, not a big improvement, it has to do with this very important parameter, AZ. So if you remember, AZ was the layer separation. There's the distance between the two layers in our bilayer system. So for such a small value of AZ, what happens in this shorter range case is that the interlayer interaction is very inhomogeneous, which destroys the collectivity. We don't want it to be inhomogeneous. So one way to get rid of the inhomogeneity would be to just increase the layer separation. That's what we do in the next part. This is just to reiterate again that at least for alpha 0 and alpha 1, we get orders of magnitude better squeezing. But we will get this for alpha 2 and alpha 3 as well once we deal with this part, which is what we do here. So here we tune the layer separation, and you see that for sufficiently large layer separation, so all of these results are for alpha 3. For sufficiently large layer separation, we actually get the exact same amount of variance that we had gotten for the infinite range case. So we get the amount of squeezing or variance with finite range that we had gotten with the infinite range. So all of these results are for a fixed system size. So I did mention scaling. So my next and last slide is about scaling. So now we directly show just the sensitivity. And if we look at the different system sizes and how the maximum achievable sensitivity changes for the different system sizes, it shows very nice scaling. Perhaps something more instructive to see would be if we directly plot the minimum value of the sensitivity with the system size. So again, I'm comparing the Fluke protocol case with the staggered case. And as expected, you see that for any system size, even for small systems, we always get better sensitivity with this solid line, which is the Fluke case. And the interesting thing is that for a sufficiently large layer separation, all the different power laws, they actually collapse. And so not only are these sensitivities better for Fluke protocol compared to the staggered field case, they also have different scaling. And the scaling is actually such that the Fluke protocol case gives us the optimal Heisenberg scaling of inverse n. So to give a summary, well, just reiterating it again. So to give you a summary, again, we are obtaining the optimal Heisenberg scaling with finite range interaction. And even if you don't care too much about scaling, even if your system is such that you don't have a very large number of spins, so for any system size, the Fluke protocol case always gives you higher sensitivity, usually orders of magnitude higher sensitivity compared to the staggered field case. And also, because if we use the staggered field case, we can actually start from very simple Ising Hamiltonian. So this really broadens our scope of which type of platforms we can use. Okay, so with that, I think I'm out of time. I'll finish, and I'd like to thank the lead of this project, Dr. Biutowski, for guiding me through this project. And our paper is in archive, and I also sneaked in my LinkedIn, just in case. And thank you for your attention. Thanks. If you have any questions.
Question? Go ahead. Anna Marie, you're more than welcome to come over.
Very, very nice. I have a question. So one of the key problems of the floquet is that you do errors when you rotate. Have you tried to add a little bit of certain percent error and see how it propagates as you do the sequence?
Yeah, no, we haven't looked at that in
That
this
would be
project
very
at all.
interesting because
But that's a very good
unfortunately,
idea, yeah.
rotations are killer for many experiments.
Yeah.
So if you know how much error you have to control to get the gain, that would be interesting.
That's definitely something that we can look at next because we're working on the second project now, very relevant to this one. So thank you for your suggestion.
The science speaker and the question. So our next speaker is